modulus of the composites. Longitudinal means modulus along this length direction, is that direction. Okay. Transverse direction is this direction. So this is L, this is T. Okay. The transverse modulus is the elastic modulus of the composites along this transverse direction, dt. And when you look at that modulus, EF, EM, why don't we have EFT, the EFL? For fiber itself, do we have longitudinal modulus and the transverse modulus? If you look at the fiber itself, do we have longitudinal modulus or transverse modulus? We don't, because we consider that is single phase material. Fiber is fiber, matrix is matrix. Isotopic material, they have the isotopic elastic modulus. Every direction, same E. So you do not have EFL, EFT, no such thing. Okay? But for composites, we will have such things, EL and ET. Different direction, modulus will be different. But for fiber itself, for matrix itself, every direction we should have the same modulus. This is so-called isotopic materials. Okay? When you have composites, it is going to be anisotropic. Anisotropic means the modulus along different direction is different. Okay? This is the definition, isotropic and anisotropic. In shear modulus, also when you have composites, you have GLT is the shear modulus, and mu LT and mu TL is Poisson's ratio. So the definition of Poisson's ratio is when you apply a loading along that direction, you have a reduction along this direction. So the reduction divided by the elongation, you get Poisson's ratio. So when you look at the composites, the reduction divided by elongation along two different directions will be different. That is why you have mu LT and mu TL. But for isotopic materials, for fiber itself, or matrix itself, just one mu. Okay, mu F and mu M. Different material, only one mu, isotopic material. So when you have fiber, matrix, and you have volume ratio, means volume fraction, because you put two materials together, you must be able to calculate what is the volume fraction of that material in the composite system. So this VF and VM is the volume fractions of the fiber and matrix. And when you have volume fraction, you can calculate the modulus of the composites. This is a modulus that you can calculate along longitudinal direction. This is a modulus of the composites along transverse direction. It is a function of volume fractions. That means if you change the volume fraction of the material systems, you are changing the modulus of the whole composite system. Right? You can tune this too. EF and EM may be constant because when you have a material, modulus is determined. Fiber, matrix is there already. But you can tune the volume fractions to tune the modulus of the composites. So this is the beauty of the composite. You can make materials. Okay? You can tune the modulus that you want. You can achieve the desired modulus or Poisson's ratio or shear modulus. And this is Poisson's ratio, major Poisson's ratio. This one is defined as major Poisson's ratio. This one is defined as minor Poisson's ratio. It is also a function of volume fraction, VF and VM. The volume fraction of fiber and composite matrix. This is shear modulus. Okay? GLT and GTL will be the same. And this one will be the same. GM and GF is shear modulus of matrix and fiber. VM and VF are the volume fraction. So I'm going to force the example.
What should give that? Top one should be like 190.
Everything else was right?
A typical composite system, the matrix is epoxy. Epoxy modulus epoxy is really very low. Toughness is high. And the fiber is carbon. So you are putting two materials together to form a composite. And this is just a cross-section. This is just a cross-section of the layered material system. You have the length along this direction. Okay? This is just cross-section. This one is 80 millimeter. This one is 20 millimeter. This one is 10 millimeter. This one is 20 millimeters. So along the length direction is 500 millimeters long. Okay, along this direction, auto plane direction is 500. And EM, the modulus of the epoxy is 5,000 Newton millimeter square. EF is 200,000 Newton millimeter square. EF, look at the modulus. Fiber modulus is much larger than the matrix. This is really true for composite system, right? You combine one very stiff material and with another very soft material together. Mu F, Poisson's ratio of the fiber is 0.3. Poisson's ratio of the matrix is 0.2. This is a Poisson's ratio. And if the loading along the outer plane direction, tensor loading, you apply a tensor loading on this composite system, that loading is 100 kilonewton, okay, along the outer plane direction. I'm asking you to determine the length elongation of the bar. So the lengthening the second thing, I'm asking you to determine the reduction of the bar along its thickness direction. The third one is the stress in matrix and the stress in fiber. Okay, thickness direction, I mean this direction, transverse direction. Okay, so this is the three unknowns I'm asking you to determine. So the first question: what is the lengthening along the longitudinal direction, not along the length direction, outer plane direction? So we need to figure out delta L equals to how much? Okay. This is unknown. We can calculate the elongation by the original length times the strength. So elongation divided by the original length, you get strength. So the elongation will be the original length times the strength. The length is here already, 500. So we need to figure out this epsilon L. And what is strain? Sigma L divided by EL. Right. Strain, according to Hooke's law, stress divided by modulus. Because you are trying to calculate epsilon L, should be sigma L divided by EL. And then, what is sigma L? Stress along that direction, you are applying a force along that direction. So force divided by area, you will get a stress along this direction, right? Force is 100 kilonewton. F divided by A. F is 100 kilonewton. A is the area of this cross section. You know the width, you know the height, right? 80 millimeter times 50 millimeters. So this one you will get 25 Newton millimeter square. This is sigma L. Force divided by the area, you get stress. And then what is EL? EL, we can use the formula now. Refer to the formula we have derived. The first one, EL equals to EF VF plus EM VM. VM is a volume fraction of the fiber and matrix. When you look at the cross section, this is a fiber, right? And this is a matrix. This is a matrix. And the height of fiber is 10. Matrix here is 20. Here is 20. Total length is 80. So what is the volume fraction of fiber? You get AF times A. Volume fraction is the volume of this fiber divided by the total volume of the matrix. But along this length direction, it's the same, right? They have the same length. So I just need to calculate the area fraction, AF divided by the A. The area of this whole cross section, AF is area of this fiber. Because along this direction, they have the same length. So volume fraction, you can calculate the volume fraction by calculating the area fraction. Same thing, EM.
Sorry, he starts showing
AM
directions, and sometimes you
divided
miss
by
the
A.
meaning if you don't see where he's pointing.
And then EF is equal to 20,000. AF, area of this fiber, length, width, and the height. Width and the height. Along this direction is length direction. Okay, so that will be 80 times 10. And total area of this cross section, 80 times 50. Right? A is the area of this whole cross section. EM, 5,000 times 80 times 20 plus 20. You have 1 M here and 1 M here. It's 40. This is a volume fraction. And then you can calculate EL is equal to 44,000 Newton millimeter squared. $200,000. We should have a zero here. Right? 200,000 EF. EF is 200,000. 200,000. 3 zeros here. I'm checking this because EL should be in between EF and EM. Shouldn't be larger than EF. Shouldn't be smaller than EM. Right? You're trying to mix two materials together. That modulus of that resulting material shouldn't be larger than the stiffer one, shouldn't be smaller than the softer one, should be in between. So your calculated EL should be in between EF and EM. Okay? So this is EL.
Check to remember.
Then
Check to remember.
you can calculate delta L. Okay? Delta L equals to L sigma L EL. L is the original length, is 500 millimeter, and the sigma L you already calculated is 25 Newton millimeter square, and EL is 44,000 Newton millimeter square. The elongation is this is the elongation along this outer plane direction. If you apply those force on these composites. And the second one, what is the reduction along the thickness direction? Thickness direction is this. This is the composites. Force is along this direction. Elongation is along this direction. Along this direction area should be reduced. So how to calculate the reduction? We need a Poisson's ratio, right? Because there's a relation between Poisson's ratio and the elongation. Poisson's ratio along this direction should be related with the elongation and the reduction. So Poisson's ratio mu LT should be equal to epsilon t epsilon L. This is the definition of Poisson's ratio. Poisson's ratio, major Poisson's ratio means the reduction along transverse direction divided by elongation along the longitudinal direction. And we can calculate mu LT first because we calculate epsilon L already. So it's epsilon T delta L divided by L. Epsilon L, you calculated delta L. Elongation divided by the length, you get epsilon L. And epsilon T is the strain along the thickness direction. Because our objective is to calculate the reduction along this direction. If we can figure out what is the strain along this direction, we know the original thickness, right? Then we can calculate what is the reduction. So we can calculate epsilon T first. Right? Epsilon T will be mu LT times delta L divided by L. If we can figure out what is the strain along transverse direction, we will be able to figure out what is the reduction. This is L, this is T. So delta L is calculated in the first step already. L is the original length. So we need to figure out this, mu LT. And then we go back to check the formula that we have, mu LT. Mu LT. According to the formula, is mu F times Vf plus mu M times Vm. Fibrous Poisson's ratio times fibrous volume fraction plus matrix Poisson's ratio times matrix volume fraction. And mu F equals to 0.3 is given. Volume fraction is, again, we can use this AF divided by A, and mu M is 0.2 is given. AM divided by A. We calculate volume fraction as we have done in calculating modulus. So mu LT will be equal to 0.3 times 80 times 10, 80 times 50 plus 0.2 times 80 times 40 plus 80 times 50. This is how we calculate the volume fraction. And mu LT will be 0.22. Look at this number. It's in between 0.2 and 0.3. So one of the properties of the composites should be in between the properties of fiber and matrix. Otherwise, your calculation is not correct. So you have mu LT, and then we can come back to calculate epsilon T. Mu LT times delta L by L. Mu LT 0.22. We just calculated. Delta L, first step, 0.284. Right? L is the original length, 500. So you can calculate the strain. Is this much. It's dimensionless because delta L divided by L, one of the units should be gone. But this is a strain along the transverse direction. Actually, should be negative. Why it is negative? Because it's reduction. Right? High force in this direction, the area around this direction should be reducing. So you can put a negative sign before this number, will just leave there. You need to understand what is the deformation. Okay? So then what is the reduction? It's epsilon T times LT. You know the strain, you know the original height, right? This is the reduction divided by the original height. You get that strain. Now you have the strain already, so you can calculate the reduction. 10 to 4, the height is 50 millimeter, right? E mu TL divided by ET sigma Y. I replace that mu with mu TL divided by ET. This equation can be derived, but it may be take you hours. I'm going to introduce that directly. It's just very similar with that one. You just rewrite those equations with some different modulus and Poisson's ratio. And epsilon t, this one will be ET sigma y minus mu LT divided by EL sigma x. Okay. This is a strain stress relation for composites. That two equations you have learned before. Hooke's law is for isotopic material, homogeneous material, one phase material. Okay. We have two phases, one fiber, one matrix. We have different modulus. We have different Poisson's ratio. So this is a strain stress relation for composites. We can write these two equations as a matrix form. Epsilon L, epsilon T will be, I just rewrite those two equations in a matrix form. Epsilon L, mu TL, T, and this one should be mu LT, EL, ET. Sigma x, sigma y. I just rewrite those two equations in a matrix form. There's a name for this matrix. It's called compliance matrix. S. Compliance or matrix of the composite system is a matrix relating the stress acting on the material system and the strain of the materials. Okay. Why it is important? Because every time you apply some loading on a material system, you are trying to figure out what is the deformation. According to the loading, you can figure out what is stress. And then use this matrix, you can figure out what is strain. When you have strain, you can figure out what is the deformation, what is the elongation, and what is the reduction. So this equation, this is how we use this equation in engineering. And this matrix is symmetry, just as what I have learned. If it is symmetry, there's a condition. So that means mu TL ET has to be equal to mu LT EL. Just the same as what I have done in Hooke's law. In Hooke's law, this matrix should be also symmetry. So symmetry is a condition for the compliance matrix. And what about shear modulus? I just derived the relation between sigma x, sigma y, and epsilon L, epsilon t. Right? So shear modulus relation between normal strain and normal stress. This equation is the shear strain relation between shear strain gamma LT and the shear stress tau xy. If you combine those three equations together,
Structure instead of micro now.
on the left we can write and there's some matrix here. This one is epsilon L, epsilon T, gamma LT. Yeah. From those three equations, I'm just rewriting those three equations. You can figure out what is the term of this matrix should be. So the first term is ET 1 minus mu LT mu TL. This term is mu TL EL 1 minus mu LT mu TL 0, and this one is mu LT ET minus 1 mu LT mu TL. This one is ET 1 minus mu LT mu TL 0, 0, 0 GLT. When you look at this row times this column, you get this equation. Right? This is just a rewriting of those three equations. We derive the three equations and then we write it into a matrix form. So we can name this as a stiffness matrix. This stiffness matrix is not the stiffness matrix you use in structure analysis. This is for stress analysis. This D is used to relate strain with the stress. You apply the stress on a system, and you want to calculate what is the strain you use. Do you have a question about this?
Did you see that D?
Do you have a question?
Yeah, the
Mm-hmm.
cyclone.
Which one? Here?
Yeah.
ET. This one is ET, that one is EL. This one is ET. So I'm going to stop here. I'm going to derive something and then do examples on Wednesday and Friday.
Top right is
So
ET.
try your best to be here because it will save time for your homework 4. Okay. Which one?
Oh, did you finish your picture?
That one is EL. Sorry, yeah. The first term, this one I made a mistake. This one is EL. The first term is EL. Thank you.
Russian. I know it.
Someday, yeah, someday.
It's crotch shot. Something like shit. It's like